at MIT, and they did some really impressive stuff there with what was this species again?
Sodium potassium.
Sodium potassium, and that was back in the day when people like me said molecules were just too messy to do anything with, and it looked like they were too messy to do anything with, but given some persistence and cleverness and hard work, they were able to do some pretty impressive stuff. And Sebastian has moved on to Columbia now, where he's making good on the impressive stuff that he told me that they would be able to do someday. And I'm happy to have you.
Thanks so much. Okay, I'll take this. Okay.
Is this working?
It's for the Zoom audience.
I see. Does the Zoom audience hear me?
We can hear you.
Okay, excellent. Cool. Well, thanks so much, Trey, for the kind introduction. Thanks so much for the invitation to be here. It's actually quite special for me to be here, to be back. It's been 3 years ago that I have been here the last time. And that was a very special seminar for me because it was the first in-person seminar that I gave after COVID. And as Charles told me at the time, it was the first in-person seminar at JQI. And you see in this room, a lot sparser. Most people were actually attending the talk on Zoom. Only the very brave ones came in with a mask. And well, I'm happy today to see a full room and people on Zoom. So this is very exciting. So since then a lot has happened in our research group, and I'm excited to tell you about our work on creating and exploring Bose-Einstein condensates of dipolar molecules. And to start this off, often people ask me, Sebastian, why do you do molecules? Trey also said that, molecules are way too complicated. Why do you bother? And sometimes I give a fancy answer and talk about quantum simulation and quantum computing, but actually in some sense, I'm excited by something much more simpler. Concurrently with the theoretical development of quantum mechanics over the course of the last century, basically there has been a persistent effort to bring more and more complex quantum systems under full control, starting with spins, electrons, photons, atomic ions, neutral atoms, and now molecules are the next frontier. And whenever we succeeded in bringing a new system under full control, it meant new opportunities for science and technology. So in some sense, we have some ideas of what to do with molecules, but I'm actually genuinely excited to see what we can do when we have molecules under full control. Allow me some local patriotism. Maybe it was I.I. Rabi who kicked off this field of quantum control. When they, in the 30s of the last century, flipped a nuclear spin of lithium, it was probably the first time a human more or less deterministically flipped a spin and controlled a quantum system. And there is actually an interesting quirk to these experiments. They actually did not flip the spin in atomic lithium, but in molecular lithium fluoride and lithium chloride. And well, you may ask then, what did we do the last 100 years to still work on controlling molecules? Well, that's because molecules are a lot more than spins. There are a lot more in degrees of freedom, including the electronic degrees of freedom, vibration, rotation, and hyperfine structure. And in particular, when we talk about controlling molecules, we are interested in preparing molecules in their lowest internal quantum state, the low vibrational ground state, because there we can hope to create molecules that are stable, at least on the single molecule level. On the theory end, it was understood early on that if we were able to control molecules, we could do a lot of exciting things. Possibilities include making novel many-body quantum systems, simulation of quantum magnetism, precision measurements, quantum chemistry, quantum computing. Several people in the audience here also have contributed to the great ideas that have been developed. And it was also understood early on that it would be particularly useful to have dipolar molecules under control. So let's remind ourselves briefly how dipoles interact. Well, two dipoles interact with a long-range interaction that depends on the distance between the dipoles as 1/r³. And there is an anisotropy of the interaction that is such that when two dipoles meet side by side, they repel each other. And then when they meet head to tail, they attract each other. And such an interaction is ideal if it's strong enough to create strongly interacting systems, and more importantly, due to the long-range character, highly entangled many-body quantum states. Dipolar molecules are in a very interesting place in terms of the strength of the interactions compared to the fairly weakly interacting magnetic dipoles of magnetic atoms, and the extremely strongly interacting dipoles of Rydberg atoms. With molecules, we have the strength of interactions of dipole moments, typically on the order of a dBi, and it's such, and we can tune it effectively, as we will see. And it's really at a regime where we can hope to tune from weak to strong interactions, where we actually, in a many-body context, expect the most interesting phases to appear. On the experimental end, the door to this research was propped wide open by the really seminal work of Debbie Jin and Jinier in 2008. They demonstrated that you can create molecules at microkelvin temperatures by assembling them from ultra-cold gases of atoms. They did that with potassium and rubidium. And of course, there's a parallel effort of laser cooling of molecules that has made tremendous progress also over the last years. But for this approach of assembling molecules, this really kicked off an effort, worldwide effort. And by now, about a dozen groups worldwide can assemble molecules, bialkali molecules in this way. But over the years, key challenges remained, which was that all groups observed in these molecular gases fast losses from collisions, sometimes termed sticky collisions. And the loss rates and the understanding of these losses, Paul Julian has made tremendous contributions to really get an understanding of what's going on. But due to these losses, it was also hard to cool the molecular gases further, and molecular gases remained relatively hot, which is still to say microkelvin temperatures, but non-degenerate. That didn't prevent people from doing exciting physics. So there's a whole range of exciting things that have been done. Also, the field of quantum chemistry was opened with quantum state-controlled chemical reactions. And actually, it was even possible to create a degenerate Fermi gas by using favorable quantum statistics and assembling molecules directly into a degenerate Fermi gas in the Gila group. However, to move on further, somehow these collisional losses had to be solved. And that, the situations change on this frontier became clear a few years ago. New methods have been developed of how to protect molecules from these lossy collisions. These include resonance shielding using molecules in the first rotationally excited state that was shown at Gila, using these first rotationally excited molecules in combination with a static electric field, and microwave shielding, using circularly polarized microwave fields to engineer a shield for the molecules. So in all these works, basically what was shown is that inelastic losses could be suppressed by a factor of 10, roughly. Or maybe, do I need to stand somewhere for the camera? Okay. Yeah, I kind of want to go over there. Exactly. Yeah. Yeah. Okay. Great. Excellent. So basically, what was shown that you can suppress inelastic losses by about a factor of 10, and for fermionic gases like KRB and sodium potassium, that was good enough to show evaporative cooling into a degenerate quantum gas, degenerate Fermi gas. However, an obvious question was, what about bosonic molecular gases? So it turns out in bosonic molecular gases, the losses are about a factor of 100 higher than in fermionic gases because collisions are not protected by a p-wave barrier through which the molecules have to tunnel. So basically, in simple terms, the question boiled down to the point whether it would be possible to achieve a factor of 100 to a factor of thousands reduction of losses for bosons to cool to degenerate gas. Basically, it need to be a factor of 100 better than for the fermions. And well, that's where our molecule comes in. We are working with sodium-cesium molecules. Initially, the key point to pick it was its strong dipole moment. It's 4.6 dBi. And if you turn this dipole moment into an effective range, you see that it can have a range of up to a few tens of micrometers. If you relate that to typical intermolecular spacings in our samples, which is on the order of a micrometer, you see that there is a route to get into the strongly interacting regime. And also at, sodium-cesium is also used in the Cancuni group in tweezer experiments, also leveraging this strong dipole moment. So let's come to the creating the BEC part. I'll give you the rundown of what we have done. So we've worked on this over the past few years. Basically all new things since I was here the last time. And yeah, so the individual steps are reported here, and I will give you an overview of what happened. So we started in an empty lab about 6 years ago. And then we set up a lot of optics and lasers and vacuum chamber. And moved towards creating overlapping BECs of sodium and cesium. It turned out, first, it seemed a bit daunting to make this new mixture. So this was actually the last bialkali mixture that remained to be studied. Not too much was known. But what we found to our, to our surprise is these BECs are miscible. The interspecies interactions are such that these BECs are actually really overlapping. And that's really interesting. You have overlapping superfluids. There would be a lot of interesting things to study. We didn't do it, but maybe still interesting, but we moved on to making molecules. So we create Feshbach molecules at a Feshbach resonance at 864 Gauss. And we just ramped the magnetic field from above to below that resonance and can associate typically 50, by now closer to 60,000 molecules.
Sebastian?
Yes.
This is Bill Phillips.
Yes.
Cesium is notoriously difficult to Bose condense. Yeah. I'm wondering if you have any insights. You sort of glossed over it like it was no problem at all. Do you have anything to tell us about magic that you performed to get this to work so well?
Yes. Thanks, Bill, for this question. I checked my talk that I gave 3 years ago. 3 years ago, I basically talked a third of my talk about how we managed to condense cesium. So it's definitely not so straightforward. So we do something quite unusual. We actually co-trap cesium with sodium in a magnetic trap, and we sympathetically cool cesium in the magnetic trap with sodium. Now, based on the wisdom from 20 or 25 years ago, it's a very bad idea to put cesium into a magnetic trap because you have spin relaxation and fast losses. But it turns out we work at sufficiently low densities of cesium in the magnetic trap that it works, and then we get very efficient sympathetic cooling with sodium, also due to the favorable collisional properties. And we can cool cesium in the magnetic trap basically without losing any cesium. This is like we have an efficiency of 20 or so. Well, it's very efficient. And then when we reach a temperature of about 5 microkelvin or so, we go into a crossed optical dipole trap with this mixture, go to the Feshbach resonance of cesium that is close to just above 900 Gauss. And there's a nice working point where you can cool cesium. You have, nimble scattering properties of cesium at this point. And there we do the sympathetic cooling in the optical trap with sodium. And then we, nature was very lucky to us that the interspecies Feshbach resonance is not far from this preparation point at, just below 900 Gauss. And we can quickly move the magnetic field into this interspecies Feshbach resonance where where we form the sodium-cesium molecules.
Thanks. That's great.
Yeah. Yeah, thanks for that question. This is, I mean, actually one of my favorite topics, because figuring out this trapping in the magnetic trap saved us a ton of time. Otherwise, you have to do Raman sideband cooling and all kinds of other things. So we made then Feshbach molecules, and then I'm also just giving you here the flash to have time for other things to talk about. Then we transfer these Feshbach molecules into the low vibrational ground state. You're using stirrup. Here in this early data, we had an efficiency of like 50% or so. By now, we have brought it up to 90% by figuring out a better transition path and so on. Okay, so with that now, we have prepared a sample of sodium-cesium molecules, 10,000 of sodium-cesium molecules, with each molecule in the low vibrational ground state. So each molecule is in the exact same internal quantum state. So we have achieved quantum state control on the internal level.
So Sebastian,
Yeah.
You didn't mention 2D confinement.
Yeah.
Was there a reason?
Yeah, we don't use, so at this point, 2D confinement. Basically, we don't need, the steps.
Well, I was thinking on the previous slide when you were listing approaches people take.
Oh yeah, I mean 2D confinement has actually been done. Yeah, that's absolutely right. So at Gila, they actually showed that you can get protection from lossy collisions also by confining the molecules in 2D. Absolutely. Yeah, I mean that has been demonstrated, but still it is tricky to initially you prepare a 3D gas and then you need to ramp on a 2D potential, and on the way to go into the 2D potential you always run into losses. So somehow, even if you hope to work in 2D, somehow you need to get there, and on the way to get there you usually have losses, and that is something you want to prevent as well. Okay. So we have now our gas of quantum state controlled molecules, and well, now we move on. Now we can exert, quantum control upon this, and that means for us microwave control of sodium-cesium to help and get also control over the external, the motional degrees of freedom. So let's first discuss what microwave control means for us. When we have molecules in the low vibrational ground state, we are here. And then we have essentially 3 microwave transition with sigma plus, pi, and sigma minus polarization at a frequency of 3.5 gigahertz to go from the rotational ground state to the first rotation excited state. A side note is that all this happens at a fairly high magnetic field, which practically, splits off the nuclear spin from the rotational spin, and really this 3-level or this 4-level structure here is all we need to care about. It's basically the high field regime. Now, if we want to control these microwave rotational transitions in the molecule, it was kind of clear to us from the start to do that in a deterministic way. We need to be able to create microwaves with a clean polarization. The real challenge here is the sigma, the circular polarization. So for that, we developed a new antenna to make very clean circularly polarized microwaves. We call it the cloverleaf antenna. It's 4 loops that can be controlled independently in terms of power and microwave phase. And with that, we reach an ellipticity of 2 degrees, which is a very good number. So almost no wrong admixture of sigma minus when we try to make sigma plus polarization. We integrate this antenna into our vacuum chamber, very close to the molecules. This is like a very thin antenna, and it's very close to the molecules, very helpful. And when we resonantly drive with this antenna, the sigma plus and sigma minus rotational transitions in our molecule, somewhat to our surprise, we found that we can reach very high Rabi couplings above 40 megahertz. So it's a really strong coupling. So if you want to think of that in a quantum information context, you can make a Hadamard gate in 6 nanoseconds. Just very recently, Simon Cornish's group from Durham, UK, reported a rotational coherence time of 60 seconds. So if you put that gate time in relation to 60 seconds of coherence time, you can make 10 billion gates within the coherence time. That's a damn competitive system for quantum information if you want to do that. But we don't want to do that, at least not for now. We want to control the motion of the molecules and cool them further. So that brings us to microwave shielding. So what is microwave shielding? In microwave shielding, we shine in a sigma plus polarized microwave field, blue detuned and off resonant. And that allows us to create the dress state, this symmetric plus stress state, which is a superposition of the rotational ground state and the first rotationally excited 1-1 state. With the detuning of the microwave field, we can control the strength of the effective dipole moment because we control with it the state composition. And in a classical picture, we can think of it as if we are setting the dipoles of the molecules in rotation with this, circularly polarized microwave field. And these dipoles then also interact. So what happens now? Well, this was proposed in early theory work. When you have these rotating dipoles, you effectively get a repulsion in all directions. So let's quickly discuss this a bit. We have rotating dipoles. All dipoles in our sample rotate with the same, frequency and phase. So when you have dipoles that rotate like this and meet on the vertical axis, they repel each other. So that's a repulsive interaction. So now what happens in the horizontal plane? Well, the dipoles rotate. When they are in one moment aligned like that, they attract each other, and they rotate a bit more, they repel each other. So somehow I need to look at the time average of that. Turns out the time average is still attractive. So you actually get an attraction. But then, then you prepare the correct dress state, some magic happens. When the molecules become close enough, the dipole-dipole interaction that mix different rotational substates. And that effectively leads to a realignment, and they continue rotating side by side. And that gives rise to this repulsive potential. So this is an energy versus intermolecular distance of two molecules. You get this, crazy repulsive potential. But, if you zoom in, you actually get, a little bit of attraction, which I described, from this, classical picture of the attraction in the horizontal plane. You get some attractive potential, very shallow attractive potential. Keep that thought in mind. So this shielding now suppresses inelastic two-body losses dramatically because molecules cannot reach the short range anymore. There's this repulsive potential. So let's see what that does for our system. So we create our sodium-cesium sample first without microwave shielding and look how long it lives. This is molecule number versus whole time. And we see decay basically in a little bit more than 10 milliseconds. Now we switch on this shielding. Well, lo and behold, we see a lifetime enhancement by a factor of 50, and the sample lives for a second. So we were extremely pleased to see that. That was already, the best improvement of lifetime that was observed for a molecule sample under shielding. And we went on to do evaporative cooling of the bosonic molecules, and we, plot here the phase-space density versus, cooling progress. Read this plot from right to left. The molecule number goes down during evaporative cooling. And first, we were very excited. We see some cooling, but then it seems we hit a limit of phase-space density. Phase-space density of 0.1 seemed to be the highest we could get. Still, objectively speaking, it was a great success. We see an improvement of phase-space density by a factor of 20, which again was the highest increase of phase-space density observed in an evaporative cooling effort on molecules, but we were stuck here at 0.1 phase-space density. So what is going on?
Yeah. Before you go on, I'd like to understand better the idea of repulsion in all directions. When we look at these molecular potential curves, we're always used to thinking about these things in terms of energy versus intermolecular distance. But in the back of my mind, I have the idea, well, it's really a potential surface rather than a one-dimensional problem. And it's a one-dimensional problem if it lacks the vector character that would allow you to get differences in different directions. But it's not so obvious to me, in spite of your explanation, why this lacks that vector character. I mean, we got lots of things that are setting directions, like the field and the polarization and all that. So could you just say a little bit more about why this ends up effectively collapsing to a non-vector situation, or a one-dimensional potential?
Yeah, that's a good question. I don't have a great intuition. I should say, though, that the curves here that are shown are actually in the S-wave channel. So there you have to be, spherically symmetric. But I don't have a great intuition, I have to say. I mean, basically, yeah, no, I don't have a great intuition.
Okay, well, I guess I'm going to take the S-wave thing as a good argument. Hard to argue against that.
Yeah. So I mean, you see that, basically this is a attraction that is spherically symmetric, right, in the S-wave channel. Yeah.
Yeah. Okay.
Yeah. So I mean, but on principle, you have to, look at it in all the partial waves, and then I think, you still get the anisotropy in. Yeah.
Yeah, I mean, it's just, I mean, there's also in the back of my mind the idea that, well, for the long range interaction, for the dipole, it's not really a good thing to talk about things like scattering length in the S-wave channel, but
Yes.
we'll leave that for now.
Yeah, but we may come back to that in some other context. Yeah. Okay, thank you for the question. Okay, let's see where we are. Okay, so we are stuck at our phase-space density of 0.1. So what's going on? Well, let's look at this collisional potential again. I pointed out to you this attractive part. And when the detuning of the dressing field is large, the attractive part is actually very shallow, but the shielding is very bad because basically the shielding barrier is not very, very tall and thick. When the detuning is small of the microwave dressing field, then the shielding is very good. You admix a lot of the first rotationally excited state, get a lot of dipolar repulsion. But then this attractive potential becomes deeper and you can get a bound state. So just, pointing out a bit the craziness of this potential. This is a potential that we engineer that has a repulsive barrier that's out at 1,000 Bohr radii. Put that in relation to the size of the molecule, which is just a few Bohr radii. And then the well depth of this attractive potential is just a few tens of kilohertz. And the binding energy of the bound state here is on the order of a few kilohertz. So it's a completely crazy scattering potential. But what we observed is that when we are in the regime of small detuning of the dressing field, which is where we get the best shielding, we actually start opening a channel for 3-body loss. That was sort of a working assumption, and we also modeled that in more detail in collaboration with Chris Green and Thijs Karman. And we actually find that recombination into this bound state, the rate of this recombination aligns perfectly with the loss rate that we see in our system that remains when we get colder and colder and work in this regime of small detuning. So we actually looked at that much more closely experimentally. We can look at the character of the losses for different detunings of the dressing field. So for large detuning, where the shielding is bad, we can look at the loss here and try to fit the loss curve with a 2-body model and a 3-body model, and we find it's very well fit by a 2-body model. So here we see 2-body losses are not suppressed yet because shielding is not good. And for small detuning, well, we see a change in character. There the loss clearly becomes, is not 2-body character anymore, it's 3-body or higher. And so somehow, this picture of recombination into this bound state is consistent, and we need to solve it. So that is what is the key to get us to Bose-Einstein condensation of sodium-cesium.
Sebastian?
Yeah.
The fits that you're showing,
yeah,
they're pure 2-body or pure 3-body, as opposed to, say, trying to fit a mixture of the two?
Yeah, in this particular one, we actually do either or, but we also have data where we do both. I show something later. We allow both, and then we see one taking over the other.
Yeah, okay, because when you look at something like the lower left, you could easily imagine that both things are happening.
Yeah, for the temperature, yes. Yeah, in the molecule. So basically, we have a model that takes into account both the number and the temperature. Yeah. So basically, yeah, I agree with you. On the temperature, you cannot have a very clear distinction. But here on this data, it's pretty consistent. I also show you only a sample of 2 runs. We did that in a very detailed way for many different detunings. So that is sort of in its completeness, the data set is very convincing, I would say.
Okay.
Mm-hmm. Okay, so let's. So where are we now? Well, we have our sample of molecules, and we apply our rotating microwave fields, which set our molecules into rotation. That gives us this problem of this attractive potential that we want to get rid of. So what could we do? Well, how about we think about inducing another dipole moment? We can use a pi microwave field and induce a dipole that is vertically oscillating on the vertical axis. So how does that interact? Well, remember, when 2 rotating dipoles meet on the vertical axis, they repel each other. If 2 oscillating dipoles meet on the vertical axis, well, they meet always head to tail, they attract each other. And so you can see that, perhaps by combining these 2 dipoles, induced dipoles, you might be able to compensate the attraction with the repulsion of the other one. Indeed, we looked at that from the theoretical end. Thijs helped us to calculate the resulting collisional potentials. And indeed, it should be possible to create a completely repulsive interaction potential while still retaining a very strong collisional barrier. Actually, early, very related ideas have been pushed forward by Alexei. Combining a circular microwave field with a static electric field, which in many ways has similarities with inducing a pi field here. So let's evaporatively cool in this setting. Well, now we start again with a sample of 700 nanokelvin. And lower the depths of our optical dipole trap in which the molecules are held. And we see, well, the temperature goes down and the phase-space density, which is basically a measure of the de Broglie wavelengths with respect to the interparticle spacing, goes up. And when we fit here this increase of phase-space density, we see an efficiency of 2. That means we gain 2 orders of magnitude of phase-space density when losing 1 order of magnitude of molecules. Well, for those familiar with atomic evaporation, that's a pretty decent number. It's a pretty efficient evaporation. And more importantly than that is, well, it seems this 0.1 is not a barrier anymore. We go here and approach the phase-space density of 1. Let's now start to look at the molecular clouds as we continue cooling. So the last point I showed you on this plot was actually here. This cloud, this is still a Gaussian density distribution. It's a thermal gas, but if we cool further, we see that a peak grows out of the middle of the cloud, which signifies the BEC. And we see here a condensate fraction of 60% and cross here the phase transition to a BEC. We can put these data points on this plot. We basically see an increase of phase-space density here by a factor of 1,000. And we cool the cloud from a temperature of 700 nanokelvin to 6 nanokelvin. The temperatures here in the condensed area are actually taken from fitting the wings of the thermal wings of the cloud.
So I noticed your BEC wasn't lined up with the thermal space.
Yes. Yeah, this is most likely, there's 2 possibilities. One is that there is basically, corrugation of the trap, and the BEC forms a little bit off center from the thermal cloud. We see sometimes things like that also for the atomic BECs, but it's still also possible you get it's the interaction effect between the thermal cloud and the BEC. So this is also possible. It's not fully analyzed at this point. But yeah, you can see that in atomic condensation is also not uncommon to see that. Okay, so for the experts, let's also look a bit at how the density and interparticle spacings relate to interaction parameters. The dipolar length of our working point here is 1,000 Bohr radii roughly. The scattering length is like 1,500 Bohr radii. So if you put all that together, you still get that this is a weakly interacting Bose gas. And that's actually important because if it wasn't a weakly interacting Bose gas, it may actually not condense. You may have too strong quantum depletion. So what we do, just to emphasize that again, what we do with these two microwave fields is we compensate the attractive potential, but at the same time, we are also compensating the 1/r cubed dipolar interaction tail. It's basically close to flat. So we actively reduce the strength of the dipolar interactions here to get a BEC. We can look at the lifetime of this BEC of molecules also, and when we hold a BEC, we can follow its lifespan, and we see a lifetime of a bit more than a second here in this data. It turns out the two-body loss rate in this sample is 4 orders of magnitude suppressed compared to unshielded molecules. So remember my question from the beginning, can we suppress the losses by a factor of 100 to 1,000? Well, we can even suppress it by a factor of 10,000. So that was quite a surprise. And I'll give you an update compared to the published paper. So actually, these BECs are, a few hundred, 200 to 300 molecules that we made in the first round of experiments. Now we have been further able to improve this. The BECs have 1,000 molecules. That's increased by a factor of 4. The evaporation efficiency is 2.6 now. That is basically the same of what you get when you evaporate atoms, evaporatively cool atoms. And a molecule number of 1,000 in the BEC is helpful because that enables very single shot imaging of clouds with relatively high signal to noise. So let's get to the exploring part here. Let me first point out something that doesn't have to do directly with the BEC of molecules, but something to do with microwave shielding. So it turns out when we apply a dressing field, we are not only changing the collisional properties of the molecules, but we are also changing the single molecule properties. In particular, we are changing the optical polarizability of the molecule because we are mixing two rotational states that have different AC polarizability. That has sort of a practical effect. It means that when we switch on the shielding field, we are actually changing the trap frequency and the depth of our optical dipole trap. That's something we need to be acutely aware of when we are evaporatively cooling the gas, because the trap may be much shallower than you think it is, and then you may have problems actually efficiently evaporating. So that's something to be aware of on the practical end. But on the more conceptual end, it's also quite cool. So basically, microwave shielding gives a control lever for the optical polarizability of the molecule. To analyze that better, we developed a spectroscopy technique to probe the energy difference between our dress states. So we call it dress state spectroscopy. We measure the energy difference between the symmetric and the antisymmetric dress state. We can also, you basically see all the transitions. So this, from quantum optics, the Molov triplet, because the lifetime of the rotational states is very long. You can see all these transitions. And you can drive Rabi oscillations between the dress states. So it's like full control. So there's another microwave field to probe the microwave dressed molecules is used here. And then we found also that with this microwave dressing, we can actually engineer a magic rotational transition between the plus and the minus stress state. So that's quite cool. That can be useful, if you think about spin physics. There have been quite some efforts recently to create magic rotational transitions with molecules using magic wavelength trapping and magic ellipticity. But sometimes it may be hard to use both these methods, and then maybe, applying this dressing field to engineer magic transition may be quite useful. Now, let's get back to our double microwave shielding. A question that we got after making the BEC is, well, you make the BEC at very small dipolar interactions. What happens when you switch back the dipolar interactions? Is the gas still stable? So, with this double microwave shielding, we have a tuning knob by tuning the balance between the sigma field and the plus field strengths. And for the BEC, we compensate them so that the effective dipole moment is close to 0. Now we can imbalance them and get the effective dipole moment and see what happens to the loss rates. We basically always find that the two-body loss rates follow the theory prediction from TIE. So I don't show the data here, but in an upcoming publications, we will show the full data set. For simplicity, I focus here on the measurements of the three-body loss rates in the system. And without shielding, we have a three-body loss rate here in the high 10 to the minus 22 centimeter to the 6 per second level. And when we make the BEC, that's here, this red point, we suppress this loss rate, three-body loss rate, by a factor of 1,000. So the question that I try to answer now is what happens in between no shielding, between the nice compensation point where we can condense. And what we find is that we, in quite a broad window, we get a suppression of three-body losses before a bound state enters, the collisional potential, and the three-body loss rate goes up. I should emphasize here that plateau here is basically technical. We see this plateau here because that is our practical detection limit. And the detection limit comes from a remaining one-body loss rate that corresponds to a lifetime of 10 seconds. So the lifetime of our molecular gas, 10 seconds, when we suppress two and three body losses as we do here in this window. So that is quite a good news. And the stability window here corresponds to an effective strength of the dipole moment between 0 and 0.7 dpi. That's also quite a nice number. It's some of the most strongly interacting dipolar gases that have ever been created. So what happens now when we increase the interaction strengths in the BEC? So far I just analyzed the loss rates when we tune the interactions. But what happens when I take a BEC and then I change the interactions? Well, there are actually several ways now with this double microwave shielding to tune the interactions. One is what I just told you. You can tune the balance between the sigma microwave field and the pi microwave field, and basically tune the interactions from dipolar to anti-dipolar. But it all has sort of this typical dipolar anisotropy that I showed you before. But in this microwave environment that we are working, we have another tuning knob. We can actually also tune the ellipticity of this circularly polarized field. Then it's not perfectly circularly polarized anymore. And that gives a preferred direction for the alignment of the residual dipole. And with that, you can create here a dipolar interaction that has this interesting anisotropy. You can describe it by a spherical harmonic Y22. And that is another way how to tune the interactions. So let's do that. Let's use this knob here. We first prepare a BEC in a ellipsoid-shaped trap, and look at the time of flight expansion. So here, the BEC is a little bit round. You see a little bit of a distortion. That's from an imperfect compensation of the dipolar interactions. And this is a time of flight expansion. So you see this BEC basically expands. Okay, so now let's turn on the interactions by tuning the ellipticity of the circular field. Well, if we do so, we see the cloud shrinks. And if you look in time of flight, we see, well, the cloud doesn't expand anymore. So this actually points to the creation of a self-bound droplet. So basically, the molecules align along the weak axis of the trap. There's attractive interactions here, and you get a droplet formation. Now we can change the direction of the interactions by 90 degrees by tuning the ellipticity in the other direction. And then we see, well, the cloud, the BEC, starts to split up and form two droplets. And well, if you look in time of flight, also these droplets don't really expand anymore. So that points to the formation of a droplet array. So, of course, and many of you are aware of this, is very much related to what has been seen in magnetic atoms over the last few years. But actually here in this regime, we already know this physics cannot be explained by mean field theory alone, by extended Gross-Pitayevsky equation. So it's a very exciting regime to be in. We also actually, just for the fun of it, to try to showcase also the level of control we have with our microwave fields, we can initially make a BEC and ramp the interactions very slowly. So we, in 400 milliseconds, tune the interactions to go from here to there. And here the molecule number is a little bit higher, so we see 2.5 droplets. And if we speed up the change of interactions, we go into a more of a quench type situation, we see that we can create all kinds of mesmerizing droplet arrays and droplet pictures. It looks quite similar to the Rosenzweig instability that was observed in the FAO group with dysprosium a couple of years ago. So with these results, let me go a little bit into the outlook. I think we are now allowed to think of this system as a new modality for quantum simulation, perhaps as a new quantum liquid. And I want to highlight a few peculiarities. So with this microwave control that we are using, we have now an instantaneous tuning knob for the interactions. We can very quickly change the range of interactions from something very short to something very long, perhaps longer than the interparticle spacing between the molecules. And we have really full control over the collisional potential. So in some sense, you can think of this as a quantum simulator for collisions. It will be interesting to study the phases of dipolar bosons in 3D. Well, the droplet physics that I showed you is already a first sign of this. It will be exciting. The question was about 2D already. It will be exciting to now, use the stability in 3D to prepare very clean 2D systems. And over the last decades, interesting phases have been predicted. What I find very exciting is to think about going to the crystal phase when the dipolar repulsion in 2D becomes strong enough. The dipoles should crystallize. And a lot of interesting phase transitions and quantum phase transitions have been predicted in this. There are also relations to excitons in 2D quantum materials, which basically expect to observe the same phase diagram. And maybe there's a way to have a nice confluence between, AMO quantum simulation, condensed matter experiments. Of course, also it will be exciting to load these molecules into a optical lattice. With the shielding, we should be able to get, and the BEC, we should be able to drive a Mott insulator transition, get a very high filling fraction into the lattice. You can also think now about situations where the tunneling is still finite because the molecules are protected with the shielding barrier. So you should be able to study extended Hubbard models in the presence of finite tunneling. And of course, when you have a unit-filled lattice, also studies of quantum magnetism in the system is going to be very exciting. So just in the last few minutes, I give you, a flash of a few other things that are happening in my group. We think about molecules, or during COVID, we thought about molecules a little bit broadly, also thinking about, what it takes to laser cool molecules. And we found actually for the example of carbon-2 molecules and OH+, that you should be able to find laser cooling schemes that are not relying on diagonal Frank-Condon factors. That is usually a paradigm in the laser cooling of molecules community, that you need diagonal Frank-Condon factors, but it doesn't seem to be an absolute requirement. So still with fairly few lasers, you should be able to cool some other molecules. And that actually triggered us to think more generally about, quantum, figuring out laser cooling or quantum control schemes for molecules. And we teamed up with Anna David at Flatiron Institute in New York City to work out approach. Initially, we thought about machine learning, but in the end, we realized a very powerful possibility is to map the level structure of a molecule onto a graph where the nodes correspond to the quantum states of the molecules, and the links between the nodes correspond to the transitions. And to these links, you can give properties, lifetime and so on, and you can run very powerful network search algorithms to figure out laser cooling schemes. We found, laser cooling schemes of molecules that have been used actually in experiment, but we find thousands of molecules more. And basically, with this method, if you have a good database of spectroscopic data of molecules, you can figure out new laser cooling schemes and quantum control schemes. And maybe this whole graph mapping is useful for other systems, not only molecules. Any quantum system with discrete quantum states should be mappable on this. Okay, we also have a setup on tweezer arrays of strontium. I just want to very quickly go through this. The goal of this effort, there's several punchlines, but maybe a more orthogonal to what other people do is our effort to create super and subradiants in these arrays. which requires that the quantum emitters, which are atoms, strontium atoms in our case, are closer to each other than the emission wavelengths. So there's two ways how to push this. One is you can push the traps closer to each other. The other one is to increase the wavelengths. And we have worked on new ways how to create tweezer arrays using holographic metasurfaces. That's complementary to efforts of using AODs and SLMs. Turns out this works extremely well. We can make all kinds of arrays, also arrays where the atoms are spaced very closely, like on the little bit more than a micrometer level. Also very large arrays with 1,000 traps can be generated with this. So watch out, we'll have a paper out in the next few days on this. We can prepare single atoms in these arrays with a fairly high fidelity. And we then work with strontium. And strontium is a very, very interesting atom, as many of you know, is used in atomic clocks and so on. And it has a very interesting internal state structure. And what we are especially excited about is transition here from the triplet P2 state to the triplet D3 state. The triplet P2 is metastable state, lives for 100 seconds. And this transition here has a wavelength of 2.9 micrometers. So that really pushes the wavelengths to larger than the interparticle spacing in the array. And, you know, we're quite excited. We just observed this 2.9 micrometer mid-infrared transition with atoms trapped in the tweezer array. So this is the spectroscopic signal. So it's ready for the next step to study super and subradiance. So let me summarize. So I'll focus here on the molecular part. We made a BEC of ground state molecules. It's the first time a phase transition has been observed in ultra-cold molecular gas. The BEC is long-lived with an extremely low loss rate. And maybe the take-home messages are that I think, you know, we can say now we have a similar level of control over molecules as we have for atoms. We have real-time control over collisions and interactions with this microwave approach. And we see the first signs of a new quantum liquid in this system. So I really want to give credit to the amazing team that made this possible over the last years. I really want to highlight the amazing work of our postdoc Ian Stevenson on the molecule effort. He's on the job market this year, so if you have a position, watch out. Also, a senior grad student, or recently graduated student, Nicola Bigali, was an amazing contributor to this. The next generation of students, Silwei Chang and Wei-Jin Yuan, already in full swing. Junior members, Hanal Kwa and Boris Bulatovic, make amazing contributions. And on the tweezer effort, we have the postdoc Bojong Seo, senior grad student Aaron Holman, and Simo Sun, and a couple of other members who already graduated. Also thanking the collaborators, the funding agencies, and I have a few announcements. So for those of you interested in molecules, we are going to have a Aspen summer workshop next summer. Watch out for an announcement. It's not officially announced yet, but the announcement should come out soon, and submit an application if you are interested in joining. It's a very nice time of the year to be in Aspen. I also want to announce this is very, very news. So we are also going to have a junior faculty surgeon AMO experiment at Columbia this year. This was just approved a couple of days ago, and the job ad should be out soon. So if there's people in the audience interested in applying, please do so, or talk to me before. So this is great news. We're very excited about that, of growing our small but very active AMO team at Columbia. So thanks so much for your attention.
Yeah, great stuff. So there are nuclear spins, right, in the molecule?
Yeah.
So you could potentially, I guess, create sort of two orthogonal states with different, like one nuclear spin on the other, and they would both be shielded, I guess, from each other and from like within.
Yeah.
I guess that won't be maybe particularly interesting because you probably won't know because they never kind of come close to each other to find out.
Yeah, but on principle, I mean, just on principle, that's possible. I mean, we basically have 32 nuclear spin states in our molecule. Currently, we just prepare one. But on principle, you can do 2 photon microwave transitions or so to prepare 2. You would think about how to decohere these 2 states, not trivial. But let's say you can do that, then you should be able to do what you suggest. I mean, there are some ideas. Actually, it was just a paper recently by Caden Hazard, Jeremy Hudson on SUN physics and molecular gases. So this, this could be of interest. I think the preprint is out. Maybe not yet. I don't know. Yeah, but these ideas. Yeah, I mean, this is possible. Yeah, definitely. Yes. Yeah.
Thank you for a great talk.
Yeah.
So one of the hallmarks of atomic BECs that I remember
Mhm.
is that they do not expand when you release them in time of flight. But here you show that by tuning the phase angle of your microwave pressing, you can get the BEC to sometimes not expand, sometimes expand.
Right.
So what's the difference?
Right. So okay, for atomic BECs, the hallmark, actually the feature that allowed detection in the first place was you see the aspect ratio inversion. When you make a ellipsoid shape or cigar shaped BEC in a trap and you release it, because it's a macroscopic wave function, the time of flight expansion basically leads to a Fourier transform of that. You get a fast expansion in the narrow axis and almost no expansion in the weak axis. And in the BEC regime, that's basically what we see here as well. If we have finite dipolar interactions, we actually see a distortion of the cloud, very strong. So this is basically, we can call it electrostriction. We're also going to have a paper on that out soon, where we analyze that in some detail. What is the contribution of the matter wave part to the expansion and the contribution of the dipolar part to the expansion? So the BEC expands, but it has this characteristic inversion of aspect ratio, which also we observe here. And then the expansion, the absence of expansion is basically when you have a self-bound state. Basically, you think of a water droplet, you let it drop, it doesn't expand. There you have, classical surface interactions, but here you have like higher order, interaction terms from quantum fluctuations that go beyond the typical Gross-Bedejevsky equation.
You're thinking of the experiments they did where they used a Feshbach resonance or near a Feshbach resonance to turn the scattering length to 0 and then drop them, and then they drop, without expanding because you don't have the mean field energy while it's falling. That's right.
Yeah.
That's probably one.
Yeah, I mean, basically, it's all, interpreting time of flight pictures is subtle. Basically, the simple inversion of aspect ratio that initially was believed to be a hallmark is much more difficult once you have actually interactions in the sample, and then all kinds of effects come in. So just thinking of it as a Fourier transform of the intra wave function, of course, doesn't really work as soon as you have appreciable amount of interactions.
I have a question.
Yeah.
These really long range molecular potentials. This might be a question for Paul. Back in the day, they used them because they're long range, none of the messy short range stuff is involved, and you can use it to calculate dipole or extract dipole matrix elements and different atomic properties that are atomic in nature, not molecular. And so they basically did a kind of interesting measure of the sodium lifetime, or equivalent to the measurement of sodium lifetime, by very carefully looking at these long-range molecular potential. But that was in sodium, and that was a sodium molecule. When you have these two species molecules, have you thought about something you could do that would be more like atomic physics? Atoms.
Yeah. Good. I mean, the honest answer is I haven't thought about it. I probably would have to look at these experiments to actually understand what's going on. Yeah.
It's a very clever idea that if you have this long range molecular potential, it's just due to the long range nature of the van der Waals, and you can extract a lot of information. But I don't know what you would extract from a two species.
Yeah. Interesting point.
It might be worth commenting in relation to Bill's earlier question. That the JQI-01 rotational transition he's microwave shielding here is formally similar theoretically to the S to P optical transitions that
Yes.
studied back in the 1990s with Bill and Steve Ralston on optical shielding with using xenon metatables in their case, where they actually demonstrated factor 10 optical shielding and atom-atom collisions due to coupling into these repulsive interactions. So it's formally equivalent,
Yeah.
except they now have these extra microwave handles for doing dual shielding and doing confined signals. Really got a little bit more complex, and they can make it much more powerful. So it actually is an analogy to the old stuff that was done in atoms many
Yeah,
years ago.
I actually should put a reference on the blue shielding in atoms on the slides. Yeah, thanks for the comment. Yeah, the ideas are borrowed, of course. From
So
this.
I remind the students that there's a tea at 4, and I encourage you to show up. And
Looking forward to see you.
Thanks, Sebastian.
Thank you.